Welcome to GeneSys. I'm Hadi Esmaeilzadeh. I'm an Hadi Chair in Computer Architecture at the University of California, San Diego. And this is our actually third tutorial about GeneSys. GeneSys is an acceleration system generator, for deep learning models. This is an effort that we have been developing since back in 2015. Multiple versions of this work has been developed, and then we have gone through generations. But that means that we're not just updating the code that we had in 2015. We're actually doing new designs, more innovative work, and we're presenting that to the community as a completely open source acceleration software and hardware stack that you can utilize in your research or in your development if you are a company. One of the good things about the work that we are presenting here is that we're not giving you a single accelerator. We're actually giving you an infrastructure that can generate accelerators and comes with a compiler that will target that generated accelerator, whatever may be your configurations. And the idea comes from the fact that, my research group pioneered the idea of template-based designs and accelerator generation, the paper that we published in HPCA 2016 that received the Distinguished Paper Award. And there has been a lot of work on, hardware generation after that work. And the idea is that, can we start from a high-level expression of machine learning algorithms and give you an efficient hardware implementation, while on the side we're giving you a compiler that can take a large variety of machine learning or deep learning models and execute it and then generate it, accelerate. And the answer is yes. The reason that we can give you both automation and efficiency, these are conflicting objectives that we're pursuing, because when you have automation, you're losing on efficiency and performance. And if you want to get, efficiency, you have to go engineer the system. The reason being is that a slew of brilliant students, some of which are actually sitting here, these people contribute to the last generation of, GeneSys, have hand-optimized design templates that are extremely parameterized and can be automatically expanded or shrunk to fit the requirements of the application or constraints of the platform that you want to deploy your workloads on. And then we actually spent significant amount of research and published quite a bit of paper on the subject matter to actually develop the compiler that gives you execution. And we've gone through the pain. I mean, not me, these students. I got the gray hair, and these guys spend the hours to actually debug the entire system to give you a correctly functional platform that actually produces the correct result. And I'm actually proud to say that I challenge you to find another platform that can run neural networks end to end. There's a lot of research that has gone to matrix operations, and you can find systolic arrays here and there that can run matrix operations, but neural networks are actually not matrix operations. They're a complicated combination of matrix and non-matrix operations. And Suruj was sitting here, and he used to be my PhD advisor. Now he is he's a doctor of his own. And we forced him to come and give a talk about it. He's going to present a critical part of this acceleration generation unit that we designed to expand the execution even beyond neural networks. And we can generate accelerators that are suitable for ultra low power edge devices. I have a project, and my students are working on brain implantable devices. We use the same GeneSys infrastructure to generate the accelerator for it and compile the workloads on that. And also generate high performance server grade accelerators that Rohan is going to talk about Wednesday for serverless computation in the cloud. Same infrastructure, right? And we generate synthesizable Verilog that you can take and deploy it on a variety of platforms. We have built a chip. My group doesn't do the backend, so we had collaborated in the DARPA real-time machine learning program that they were taking care of. We generate the Verilog, they take it, and since they fabricated the chip, we had a successful tape out of the chip. And since we were working with this group, the design has been done in such a way that you get, if you were to go and fabricate a chip, you're going to get high frequency. I think we got around 1100 megahertz, right? 1.1 gig, which is quite impressive for an accelerator at this scale. And there has been a lot of design considerations to make sure that your clock frequency is going to be high. At the same time, you can take the Verilog code, and we have all the apparatus, and deploy it on a variety of FPGAs. I think we are targeting three different FPGAs, one of which is the Amazon F1 instances. You can actually take the code that we generate and the compiler that we give you with, and go to Amazon and deploy it on F1 instances and do your cloud-based research. Why we are doing these tutorials? The reason being is that the world is moving towards, kind of collective acceleration, let's call it, rather than individual, accelerators that are working on one workload. Even if you take any of the large language models, inferencing on a large language model is kind of impossible to do it on a single chip, because memory constraints, compute constraints, and things like that. If you want to go training, then you need to have massive number of accelerators. And we are in TPU version 4, or they're probably working on version 5 that they have already assigned, announced 5. So we kind of know how to design the architecture of the accelerator, except for that tandem processor that Surush is going to talk about today, and also Tuesday in the main tracks of the conference. So we know how to design individual accelerators. It's time for us to take these innovations that have led to building these and go do system research that seamlessly integrates this, these accelerators, not only in the infrastructure of the cloud, but also in the system software that abstracts cloud out. For instance, our system community and counterparts have done an amazing job on abstracting warehouses of computers as function calls. That's serverless. Or you just see the cloud as a Kubernetes cluster, and you reserve it, and now you're just running programs. What is happening is that behind the scene, there is a humongous amount of innovation that is giving you that, that abstraction. So, but the system research community, the way that they operate is that they take the hardware as available, then they do the system software on it, right? And that's why their research is more immediately applicable. You can actually use their innovations. Maybe your PyTorch is going to run, faster with a bunch of GPUs. We, on the other hand, as computer architects, we get the privilege to modify the hardware, the infrastructure, the architecture, all of that. And then we can go and permeate these changes that we are making to the to the rest of the system. And now we're dealing with the era that we really need to deal with scale-out systems. And the innovations that seems to be very exciting is that how do we change different parts of the system stack while I get to modify the architecture and imagine a new scale-out data center or even a node for ourselves. But to do that research meaningfully, you really need to have functional units that lend themselves to you so that you can actually modify them, change them, or run your workloads on them so that you can do the rest of the innovations that you have. Well, we've been working on this, this is probably the third generation of this release that we're doing. For the past 10 years, we have put the effort for you. Now you can take it, you can run your workloads on it, and you can build innovative systems. While this gives you an ability to actually work with a real open source modifiable functional acceleration node. And that's what Rohan has done in his own work, that taken this infrastructure and done serverless research, near storage serverless research, that brings about a completely new concept in terms of how you can perform serverless computation. And while my research group has pioneered open source hardware artifacts, generally speaking, especially in the domain of machine learning. And the reason for that is that as an academician, I took it upon myself to initiate this cycle of open sourcing within the community, because if you think about software development and how that is fast and vibrant, is that, well, right now, if you're doing programming, you're probably composing a large list of open source libraries to get an application done. Do we have that in the hardware community? The reality of it is that there is some efforts like RISC-V, very inspiring. NVIDIA was the, NVIDIA did, but they're not supporting it that much. And then we're bringing this to the community so that there is another point, especially in the frontier of the workloads that we care about. And we have components within it that can expand the domain of acceleration beyond neural networks. Even within the neural networks, this is the only platform that can run neural networks end-to-end. And then these fantastic students, really brilliant. I can't even imagine, how much effort that has gone. Imagine getting a software system working. How hard that is. I know that people go through artifact evaluation. I don't go through artifact evaluation, actually, to be honest, because we just don't have the time. We'd rather contribute to the open source project and give it to you guys to go and build your own systems. I'm not against it, but we just don't have the time. In a scale that you can actually take it and run it on Amazon F1 instances, and you get the compiler that runs the code for you correctly. Just compare that with software development itself, you would realize how much effort that's gone, and we are amortizing it for you. So that you can go, for instance, focus on your CXL research that we're doing. Coming up with new distributed, scheduling algorithms for the LLM workloads that you want to support. Think about, LLM serving in a different domain. Even go do security research related to real work, that is running on the hardware. And if you want to even build a chip, this is available. You can start from here. And we are continuously updating, changing the architecture. We have actually a programming language for cross-domain. When I say cross-domain, I mean, well, we had CPUs and we had the general purpose programs that we were writing, and everything was running on the CPU. Then everything becomes domain-specific architectures, and if you are doing anything, you have to go find the language, the compiler, the hardware, and do it. And usually it's not even available. There's a bunch of papers that says, if you do this, this is how much you're going to get performance out of it. So there is this pendulum has swung from one extreme to another extreme, that you were running everything on one platform. Now, if you want to run anything, you have to have its own platform. There is a research area here, which is multiple correlated domains that can give you an end-to-end application execution. I'll give you an example. If you're doing self-driving cars, You have to do significant amount of digital signal processing to do sensor fusion. Then you have multiple neural networks that you're doing, perception, segmentation, whatever. And then you have to do control algorithms to do the control, actually. That's an end-to-end application, which is not just a neural network, right? So you need the language, you need the compiler, and Chris is working on a language we call Phi. And what we have done is that we are doing a glass house design. So we have design documents, we have discussions, it gets posted immediately after the meeting. Not only we are, open sourcing the code, but we are giving you first-hand, access to our thoughts and design processes that goes to developing that language. And if you engage, you can influence them, right? So that's another effort that is, continuously going. So I